Here is a graph of a continuous and differentiable function f(x). We are going to choose any two different points on the graph. Any 2 points mean no matter which points. For example, I can choose these two. Now I'm going to connect the 2 points by a line and find the slope of this line and call it m. What is m? M is the rise over run. The rise is the difference of the y's, so it's f of b minus f of a, over the run, which is b minus a. Now we would like to find at least one point between a and b on the curve of y equals fx, for which the slope of the tangent line is also m. It means that the tangent line is parallel to the first line. Let's see. For example, we can take this one. If this is C, and it's also true here, and if this is D, then if you look, the slope of the tangent line at x equals C and at x equals D in this case is m, because the tangent lines at x equals C and D are parallel to the line between AFA and BFB. It means that m equals f prime c. It means that m, which is also f of b minus fa over b minus a, equals f prime c. The same is true to d, because there is a theorem that will tell me that there is at least one point C like that. We conclude that if f is continuous and differentiable on the interval ab, then there must be at least one value of x, for example the value c, between a and b, such that f of b minus fa over b minus a equals the derivative of the function at x equals c. The question is this is really always true? And the answer is yes. This is the mean value theorem, in short MVT. It's not only that we were lucky now that this really was true. This is always true. So here is the mean value theorem. It is true with the given conditions. What are those conditions? Let f be a continuous function on the closed interval ab and differentiable on the open interval ab. Then there is a value c between ab such that f of b minus fa over b minus a equals the derivative of the function at x equals c. There is a better way to write this one. Multiply both sides by b minus a, and we get that f of b minus f of a equals f prime of c times b minus a. So another way to actually view the mean value theorem, it's that everything is the same, but in the end, instead of this equality, I'm writing this equality, which is f of b minus fa equals f prime c times b minus a. I would like to note that f must be continuous on the closed interval, otherwise there is no guarantee to have such c as in the theorem. For example, you can view this. If I will take these 2 points a and b, I will connect them. If you can see, there is no such point at which the tangent line is parallel to this line, and the point is between A and B. You can see that there's no point here like this, and there's no point here like that. But also, I would like to note that f must be differentiable on the open interval. Otherwise, again, the theorem will fail. An example. Here is a and here is b. And as you can see, the function is not differentiable between a and b because there is a sharp corner there. Let's connect the line. Okay, this is the interval AB, and now I'm going to do exactly as before. I'm going to check. None of the points on AB which are above. And now I'm checking here, nothing. Which means we really have to be picky about those two conditions. First, the function is continuous on the closed interval AB. Second, it is differentiable on the open interval AB. Example. Apply the mean value theorem to the function fx equals x cubed minus 10x minus 2 on the closed interval -1, 3. First by using the graph, and then by applying the theorem directly. First, let's use the graph. Here is the graph of this function. Let's find the points at which x equals -1 and x equals 3. Here is this one, and here is this one. And let's connect them with the line. You can observe easily that exactly here there is a point between -1 and 3 for which the tangent line is exactly parallel to the green line between the 2 points. And we can roughly observe that this value of the x is almost 1.5, not exactly, but looks like almost like, 1.5. And obviously 1.5 is greater than a, which is -1, and smaller than 3, which is b. We're now going to do this analytically. So first, let's start with substituting fb minus fa over b minus a when b equals 3 and a equals -1. We will find f of 3 and f of -1 by substituting 3 and -1 in the function f. We have this. And we get that, -12 over 4, which is -3. And this should be equals to f prime c. So we differentiate the function and substitute c and solve for c. So f prime of c is 3c to the power of 2 minus 10, and I want those two to be equal. So we can solve that. Let's do that. We get plus minus square root of 7 over 3, which is roughly plus minus 1.5275, okay? And obviously we need to pick the value of c, which is between -1 and 3. So in our case, because c is between -1 and 3, we will take c to be the square root of 7 over 3. So the exact answer for c is square root of 7 over 3. And we can conclude that f of 3 minus f minus 1 over 3 minus 1 equals the derivative of the function at x equals square root of 7 over 3. Example. Apply the mean value theorem directly to the function f(x) equals x to the power of 2 plus 5x on the closed interval 0, 6. So we just have really directly to apply the theorem, and a equals 0 here, and b equals 6, and the function is x to the power of 2 plus 5x. So as before, what is f of b minus fa over b minus a is f of 6 minus f of 0 over 6 minus 0. And we get that. We are going to do the numbers, and we get 11. On the other hand, the derivative of the function is 2x plus 5. So f prime c is 2c plus 5, and we want those two to be equal. Let's solve for c. 11 equals 2c plus 5. And we get that c equals 3. This is not enough. We have to check that this value is between 0 and 6. Of course it is. So we conclude that f of c minus f of 0 over 6 minus 0 equals f prime 3, and 3 is obviously between 0 and 6. Example. Let f be a non-continuous and differentiable function such that f prime x is greater or equals to 2 or less or equals to 5. If f of negative 4 equals 2, what are all possible values of f of 3? This is a typical mean value theorem problems. We are going to apply it, and if you look, we have to find the interval a and b, but since it is given that f of negative 4 equals something and we are looking for f of 3, we are going to take a to be negative 4 and b equals 3. We just tried the theorem, and now we are going to fill in with the values. b is 3 and a is negative 4, and we get that. Now I'm going to use the fact that f prime of x is greater or equals to 2 and is less or equals to 5 to all x. But c is the value of x. So f prime of c is also greater or equal to 2 or less or equals to 5. It means that this is between 2 and 5. Now I'm going to replace what is given. It is given that f of negative 4 is 2. So I'm going to replace this by 2. And with your permission also, I will calculate 3 minus 4 to be 7. Now I have to solve that for f of 3. We'll multiply everything by 7, and we'll add now 2. So we get that f of 3 is greater or equals to 16 and less or equals to 37, which means that all possible values of f of 3 are between 16, including 16, and 37, including 37.